Plates, Proofs, and Probabilities by Jacqueline Campos,
Kyra Grafton.
and Isabel Lopez.
In this presentation, we are going to go over a little bit of history and why we decided to route our project towards tectonic plates and how it affects us as historians. Then we are going to show you how we use probability to find the chance of an earthquake with the help of a graph theory as well. We will also be going over potential risks and planning based on what we found using dimensional analysis. And then we are going to go over some cross-disciplinary discussions. To start it off, we chose to base our math off a serious environmental issue that directly affects us, and that is the Cascadia subduction zone. This directly affects our area as this fault line could cause astronomical damage on the coast from Northern California to Canada, and we are right in the line of fire being on the coast. So we thought it'd be interesting to dive in and see how mathematicians and scientists find out exactly how this can affect us. It's serious because the last event in the Cascadia region occurred more than 320 years ago on January 26, 1700. This event is supposed to occur every 200 to 500 years. Now we can get into the math of it all.
So, annually probability, so a lot of scientists estimate that a 37% chance of a magnitude 8 or plus earthquake would be probably hitting us in the next 50 years. We were like, okay, let's break it down, maybe the first few years, and then we will see what the 50th year would look like. So the equation we found was P, which is the quake in n years, or I guess times it by the earthquake in n years, equals 1 minus parentheses 1 minus P to the power of n, is the basic probability formula when it comes to these steps. As you guys can see here, we kind of broke it down what kind of everything stands for. P is the probability of the event happening, which is a 0.0092. And then the 1 minus P, we're not really going to look at the next one because it's the probability of not happening in the certain amount of years. So we're going to skip down to the bottom and see final subtraction from 1. And that is our formula, the 1 minus parentheses 1 minus P to the n. In this next slide, we're solving for the first 5 years, and then we're skipping to the 50th year. Here, as you can see, again, the probability of a magnitude 8 or plus in the Cascadia zone in the next year, or I guess 50 years, would be the 37%. And right here, we did round these up. So in 2 years, once you do the math, the 1 minus, open parentheses, 0.9908, which is what we got here in our equation at the top, over the power of 2 for the 2 years equals a 0.0183, which, once you put it into a percentage, equals 1.8. We did go ahead and round these up, so we were able to graph it. And if you go over to the 2 years, it's a 2%. We did that so on and so forth for the 3rd year, which would be the 2.7%. 4th year is 3.6. 5th year is 4.5. And then down to the bottom one, we can see there that it is a 37% for the 50th year.
Given that the probability for an earthquake is so far and few between, we are even more so at risk for a tsunami of sorts, or maybe even small ripples in the ocean. So on that note, we're going to look into how fast does a tsunami travel, just so we can kind of get an idea of how fast something like that might happen and how we might need to be prepared. We're going to take the gravity, how strong gravity pulls, and the ocean depth, and we're going to do a dimensional analysis equation to find how fast a tsunami could travel. We're going to take the speed equaling the square root of gravity times depth. Plug in the numbers. Speed, square root 9.8 times 4,000, multiply inside the square root, equaling 39,200. Take the square root of 39,200 and that'll give you around 198 meters per second. Change meters to seconds into miles per hour. We have our conversions noted there. And after we do this and cancel out meters per second to miles per hour, we get 443.0080796 miles per hour. So about 443 miles per hour. That's just about as fast as a jet plane. Deeper in the ocean equals faster tsunami. In deeper waters, tsunamis travel faster. They can travel extremely fast. Shallow waters slow down tsunamis as tsunamis approach land, often why we would not see a small ripple of a tsunami in the ocean at a lower degree. But to find out more on how that might affect us, we're going to learn about what the impact of something like a disastrous thing like a tsunami or an earthquake could cause.
So the next part would be our cross-disciplinary integration. Back to what Jacqueline said with the destruction that it could cause. Some of the other things that would fit into this category in math would be coastal engineering, because they're the ones mapping out coastal protections, designs, infrastructure designs. We have some social science and policy, and then some understanding of the tectonic processes. And we're not really going to go ahead and look too much into that, but let's go into the math part, which is the fun part. I really based it almost on the side of just economics and policy. As you can see here, we went ahead and did some probability. We started off with it says here, vertical evacuation tower that is roughly around, would be the cost of like 2 million to protect. Oh, I just realized this is actually wrong. It's supposed to be 12 million, because then at the bottom we have 12.5 million. Do you guys see that?
It's okay. I'm pretty sure I said 3,200 and then said 1,000 afterwards earlier. So
That's
we could
okay.
fix it.
Maybe.
How long did we take recording wise? Just out of curiosity.
We're at 7.18.
7.8. That's pretty good. Cool.
I wonder if we can crop it and then start halfway through, but maybe not.
I don't know what's going on. Ah, dang internet.
Let's see here. Stop recording. Stop.